Welcome everybody. This is our 13th class in JEE mains previous year questions for chapter Moving Charges and Magnetism of class 12th. Before this video in this series we have made 12 videos and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET previous years, so you can go to our channel and can find those videos out. And if you find these videos helpful, useful, then you can press the like button, share them as much as possible, and subscribe to our channel. Also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of donations will be highly appreciated. So with this, let's start today's video. And previously, I think we were around 90 or something. Yes, this was the last question which we covered, and today we will go with start with the next one. So let me adjust pen thickness. So current of 10 ampere and 2 ampere are passed through two parallel thin wires A and B respectively in opposite direction. So as current is in opposite direction means they will repel each other. Wire A is infinitely long and length of wire B is 2 meter. The force acting on the conductor B, which is situated at a 10 centimeter distance from the A. So A here is infinitely long. So we can say, okay, we can draw a diagram here, that A will look like something like this, infinitely long conductor, and B we have of some certain length, of specific length that is mentioned to be 2 meter. So this distance is 2 meter and their separation is 10 centimeter. So we have to find out the force acting on the B conductor. This is B, this is A. Or even if they ask that force acting on the conductor A, then even we can find out, because forces are equal and opposite. Force acting on B is equal to force acting on A. So we can just find out using that method. And we know that force acting per unit length on this conductor B will be given by the magnetic field of the A multiply its current. So magnetic field of A is mu naught by 2 pi into current flowing into A divided by the distance, that is 10 centimeter. So 10 into 10 raised to power minus 2 multiply by the current of conductor B, that is 2 ampere. I think it does not matter 10 or 2 because both are there. So force will be 4 pi into 10 raised to power minus 7 divided by 2 pi into 10 into 2 divided by 10 raised to power minus 1. So this gives us 2 into 2 4. Here we 10 raised to power minus 6. It will give additional. So 4 into 10 raised to power 5. I think it should. And it is force per unit length. I forgot the length. So it is force per unit length. Now length of the conductor B is 2 meter. So force will be into length. Putting value of length is equal to 2 meter. We will have answer 8 into 10 raised to power 5 Newton. So option A will be the right answer here. Moving to the next one. The circuit consists of the wire at a top and bottom are identical spring left and right side. The wire at the bottom has a mass of 10 gram and 5 centimeter long. The wire is hanging as shown in the figure. The spring stretches 0.5 centimeter under the weight of the wire, and the circuit has a total resistance of 12 ohm. When the lower wire is subjected to a static magnetic field, the spring stretch an additional 0.3 centimeter. The magnetic field we have to find out here. So first let's discuss regarding the without magnetic case, or we can say without magnetic field. So in this case, it is mentioned that spring stretches by 0.5 centimeter under the weight of the wire, and as we can see that these two springs are in series. Both of these two springs are in series. So suppose uh, spring constant of first is k, then second is also k, because both are identical, and they are stretched by a, we can say, a amount that is 0.5 centimeter. They are stretched by 0.5 centimeter. So total restoring force of these two wires will be upward, and weight of wire is downward, that is mg. So we can say twice of kx is equal to mg. Now weight of wire is given 10 gram. We know the extension in the spring, that is 0.5 centimeter. So we can find value of k. So it will be twice k 0.5 by 100 is equal to 10 gram mass of wire into kilogram into gravity. So here 100 we can cancel out, or we can write it 0.5 by 100, we can write it like twice k 5 by 1000 is equal to 10 by 1000 into 10. So 1000 get cancelled, and 5 into 2 10, and 10 get cancelled. So from this we can say that value of k, or spring constant, is 10 Newton per meter. That's the spring constant. Now let's move to with magnetic field. Now let's first of all find out the current in the circuit, because there will be some current flowing in the circuit. Only then we can have effect of magnetic field. So current will be I, potential, that is 24 volts, and by the total resistance of the circuit, that is 12 centimeter. So that is 2 ampere. 2 ampere current is flowing in the circuit, and direction of current will be something like this. Let's first clear these. Now we are discussing the second case. So direction of the current will be from the positive to the negative. So it will be here. Here in this spring we will have upward direction, and in the wire, direction of the current will be in the positive x direction. And magnetic field, we don't know, but it is mentioned that when we apply a magnetic field, the spring gets additionally stretched by 0.3 centimeter. So if springs are stretching additional, means magnetic force, the force due to magnetic field, should be downward. So now we know that for a current carrying conductor, we know magnetic force is given by I into L cross P. Now we know, now we only looking into direction. So direction of magnetic force is minus y, or negative j, I as it is. Now direction of length, it will be the direction of current, and it is in x direction. So I, so what will be the direction of magnetic field? We know if we put here k, I cross k will be minus j, because k cross I is j. So here magnetic field should be in the k direction, or in the positive z direction, or out of the page. Means option A is possible and option D is possible. So B is out of page. Now coming to the stretching part, that there is additional stretching of 0.3 centimeter. So we can say the additional magnetic force, the magnetic force that is causing additional stretching should be equal to twice of K into X dash, where X dash is the additional stretching, K is the spring constant, and because we have two springs, that's why we added 2. So magnetic force will be equal to twice, K is 10 that we know, and value of X dash is 0.3 centimeter or 0.3 by 100 or 3 by 1000. So magnetic force is 6 by 100 Newton. Now using this, as we already know that magnetic force in magnitude should be BIL, and it is 6 by 100. B we don't know, value of I is 2 ampere, and length of this conductor is 5 centimeter. So 5 by 100. And using this, we can say magnetic field is 6 by 10 or 0.6 Tesla, and out of page. So option A will be the right answer here. Moving to the next question. A current loop ABCD is held fixed to a plane of the paper as shown in the figure. The arc BC, radius is equal to B, DA, radius is equal to A of the loop are joined together by two straight wires ABCD. A steady current I flowing in the loop. The angle made by AB and CD is 30 degree. So another straight wire with steady current I flowing out of the page is kept at the origin. The magnitude of magnetic field due to the loop ABCD at origin. So we have to find out magnetic field due to this loop ABCD at the origin. So let's slide it down. Now we have here two type of structures. First we have straight lines or straight wires, I can say. Straight wires which includes AB part, this part, and DC part or CD part, AB and CD. And we have two arcs, and these arcs are A to D, or if we take the direction of the current, that is D to A or DA, and B to C. We have these two arcs. Now as we can see from the diagram that this point O lies in the axial, lies on the axis of this line AB, and O point also lies in the axis of line DC. So due to segment AB and CD, there will be zero magnetic field. Why? Because point O lies on its axis. If it has been somewhere on the equatorial axis or somewhere between normal axial and equatorial and somewhere in the between, then it will have some value of magnetic field. But in case of axis, there is no value of magnetic field because both of the angles reduces to 0 in this formula. For a straight conductor, we have formula of magnetic field, that is mu node by 4 pi d into I sine of phi 1 plus sine of phi 2. In case of axial point, the value of phi 1 and phi 2 is 0. So this whole value, formula reduces to 0. Now coming to the arcs. As these arcs are part of a ring or a loop. So for a loop, we know magnetic field is given by mu node I by twice of R, and this is the value of magnetic field for a complete loop. And here we have a part of loop, that part is include only spans up to 30 degree. So we will divide this magnetic field due to a whole loop into 360 degrees, because a complete loop includes 360 degree or covers up to 360 degree, and we have only 30 degree available here. So magnetic field due to these two arcs formula wise will be mu node the current to this will on 12 24 R. So this is the value of magnetic field. Now let's find out value of magnetic field due to arc AD. So BAD, it will be mu node assuming current I by 24 and distance from point O is A. For arc AD, it is distance is A, so it will be A. And now direction. Using right hand screw rule, we can find out that magnetic field at around arc AD will be something like this. That on the left hand side, it is coming upward, and on the right hand side, it is going downward. So this field will be out of plane. Now, for the second part, or we can say the second arc, BBC, magnetic field will be mu node I by 24 times the distance. Distance between O and B, O and C, we can say it is small b. So small b. And now using right hand screw rule, we can say that direction of the magnetic field will be something like this. On the right hand side, it will be going downward, and on the left hand side, it is going downward, and on the right hand side, it is going upward. So due to arc BC, magnetic field at point O will be into the page. So this is into the page. So net field will be their vector sum. One is out of the page and second is into the page, and this field will have larger value, as in this case value of A is smaller as compared to B. So here denominator is smaller, so this field will be larger and this field will be smaller, and our net field will be out of the page, and value of net field will be mu node I 24A minus mu node I 24B, or we can write it mu node I by 24 1 by A minus 1 by B, that will be B minus A by AB, and that is option A. So option A will be the right answer. Moving to the next one, I think, okay, here we have statement is same, but the question is different. Due to the presence of the current I1 at the origin, the forces on AD and BC are zero. Forces on AD and BC are zero. These are the statements. The magnitude of net force on the loop is given by this. Magnitude of net force on the loop is given by this. The forces on AB and DC are zero. So in all of the option, it is mentioned that we have to find out value of force. So let us discuss, let's find out value of forces on all these these two straight conductors and these two arcs due to current I1 at the origin. And as mentioned that at the origin, there is a straight wire. There is a thin straight wire in which current I1 is flowing. So due to this straight wire which is at center and it has a current I1, so value of magnetic field around it will be given by mu node I1 by 2 pi d, and direction of this current, and this current is flowing out of the plane, means coming out of the plane, something like this. So what will happen? With the help of right hand screw rule, we can find out that direction of magnetic field will be clockwise, anti-clockwise, sorry. This is something like this. Magnetic field will be something like this. Now we will find the value of forces. So first let's come to the force on AD. Force on the arc AD, that will be I. This I is the value of current in the AD into L cross B. This B is the magnetic field due to the wire which is at center. Now, as we can see from the diagram that this arc is also circular and its center of this arc is O, and magnetic field lines are also circular and their center is also O. So means these magnetic field lines and this arc, they are moving parallel to each other. So their angle is 0, and if their angle is 0, then we will have here sine of 0, and sine of 0 is 0. So on AD net force is 0. Similar for the BC, as center of arc BC is again point O, and it is moving anti-parallel to the, here current is moving anti-parallel to the magnetic field lines, means here theta is 180 degree, and again in case of theta 180 degree, cross product will be 0, so magnetic force will be 0, and that is our statement A, that forces on AD and BC are 0. Now coming to the other part, that let's see the statement D, that forces on AB and DC are 0. That forces on AB and DC are 0. Let's find out force on AB. Now first of all, to find out the value of force on AB, we can see from here that here magnetic field is variable. From point A to B, magnetic field is variable, and direction of current and magnetic field, which are both are perpendicular to each other. Let me draw it clearly. Here magnetic field lines are moving something like this, and current is moving like this. So in magnetic field and current there is angle of 90 degree. Means according to this formula there will be certain value of force, but it will not be easy to calculate the value of force. Why? Because between point A and from point A to point B there is variable magnetic field. So what we have to do for that? We have to take that question, that part will be solved using integration. But we are sure that value of force will not be 0 for neither AB and no DC. So statement D should be wrong. And B and C we don't have to solve, as we have already solved A, and it is the right answer here. Now let's move to the next one. Two long conductors separated by a distance D carry current I1 and I2 in the same direction. They exert force F on each other. Now a current in one of them is increased 2 times and the direction is reversed. The distance is also increased to 3D. The new value of force between them. So initially force will be, or we can say force per unit length between them is equal to mu naught by 2 pi I1 I2 by D, as they are carrying current in the same direction. So now suppose after the changing the variables, reversing the direction of the current and increasing and that stuff, new force is F dash, and that is also force per unit length. It will be mu naught by 2 pi. Now current in one of them is increased 2 times. So suppose I1 becomes 2I1. It does not matter which one increases, as both are in multiplicative, and direction is reversed. So suppose direction of I2 is reversed, so we have a negative sign here, as I2 becomes negative. And now the new distance is 3D. So new distance is 3D. So now we can write it like this, that minus 2 by 3 mu naught by 2 pi I1 I2 by D, and this part is equal to F by L. So our new force per unit length is equal to minus 2 by 3 times of the old force per unit length, that matches with option A. Let's move to the next one. If current is passed through a spring, then the spring will. So what will happen to the spring? So let us draw a spring. Suppose this is a spring we have, and this part is in the front side of the screen, and this is on the back side. So let me write, this is in the front side, this is in the back side, this one is in the front side, and this one is in the back side of. So suppose this is the direction of the current. It is coming from the back side, going from the front, then from going to the back, and then coming to the front. As well, we can see that in case of two front sides, they have current in the same direction, and similarly in case of two back sides, they have current in the same direction. And we know that when two parallel conductors have current in the same direction, they attract each other. So these two sides will attract each other, and similarly for the upcoming sides, they all will attract each other. So in short, our spring will compress. So option B will be the right answer here. Let's move to the next one. So wire 1 and 2 are carrying current I1 and I2 respectively, inclined to theta each other. What is the force on the small element dl of wire 2 at a distance r from wire 1 as shown due to the magnetic field of the wire 1? So due to magnetic field of wire 1, we have to find force on a small element here, that is dl, and at it is distance r from the we can say at distance r from the first wire. And now assume that these two wires before meeting here are infinite wires. So that extend them, that it is an infinite wire and it is also an infinite wire. Now if this is an infinite wire, for this point of this small element dl, we have one angle, that is theta, and we can also assume that there will be another angle, that is phi. So magnetic field at this point will be B will be mu naught by 4 pi d into current of the first wire, because first wire is producing magnetic field, sine of phi plus sine of theta, sine of phi, sine of this angle we have to take, that is 90 minus theta, that should be 90 minus theta. And direction of the magnetic field will be, using right hand screw rule, we can say that direction will be into the page, or we can say if we draw the axis like this, that it is x, it is y, and this out of the page is z, so it will be negative k. So direction of the field will be in the negative k direction. Now for an infinite wire here, that phi is almost 90 degree, so it will be 1, and this will be sine 90 minus theta is cos theta, and distance is r, so we can say it will be mu naught I1 by 4 pi d 1 plus cos theta of negative k. Here we took an assumption that is an infinite wire, but it is not as such mentioned anywhere. So what we take, we keep sine phi as it is, so that if after solving whole, if we find it suitable, then we can put consider it is infinite wire. So till now we will consider it as it is, so sine of phi will stay as it is. Now we have the value of magnetic field. Now coming to this dl part. So our dl is something like this. This small element is something like this, and here with vertical it is making angle theta. So this angle will be 90 minus theta, and this element length is dl. So we can break this element length dl into its component, in the x component and in the y component. So our dl vector will be dl cos 90 minus theta in the x direction, or we can say dl sin theta in x direction, dl sin theta in x plus dl cos theta in y direction. That's the our length component. Now we can simply find out the force. We know that force is given by I L cross B. Current in the conductor, that dl is I2. Length is this one, and what we do here, we take dl common. We take dl common. We have sine theta of I, sorry, sine theta of I plus cos theta of j, and cross product with magnetic field. Our magnetic field is this one, mu node I1 by 4 pi d, and d is equal to r, so we put r here, with sine phi plus cos theta negative k. So let's write them. It will be mu node I1 I2 dl by 4 pi r into sine of phi plus cos of theta. Now going to the cross product, I cross k, I cross negative of k, we have I cross negative of k, that we can write it like k cross I, and that will be j. So sine theta j, sine theta of j, and now going to j cross negative k. So we have j cross negative k, j cross k is I, so it will be negative I, and here we'll have cos theta with negative I sign, cos theta with negative I sign. What is, yes. So in the answer it is only magnitude. In answer it is only magnitude. So let's take magnitude. This whole term will stay as it is. And if we take magnitude of this will be sine square theta plus cos square theta, that will be 1. So magnitude of the force will be mu node I1 I2 dl by 4 pi r sine phi plus cos theta. So let's now come to the assumptions, that what assumptions we have to make. Now, okay, so yes. So one mistake we made here, and let's correct that. If we are taking this angle theta, okay, sorry, no mistake, because we took sine 90 minus theta, and phi is as it is. Now let's make the assumption that conductor 1 is an infinite case. So in that scenario, we can say, where is hand here? In that case, phi will be 90 degree, and if phi is 90 degree, then our magnetic force will look like something like this: I1 I2 dl by 4 pi r into 1 plus cos theta. And we don't have any such option here, but what we can do, we can split this into two parts, that mu node I1 I2 dl by 4 pi r plus mu node I1 I2 4 pi r cos theta. This is a constant part because all the values are constant, means not changing. Only here we have theta variable. So we can match F magnetic force to this value. And here we will have option. We have some option here. It does not look like that. So either none of the option matches, or there should be by 4 here. There should be by 4, only then we can say this option partially matches. So that was the question number 95. So with this we end this video here. Again, if you find this video useful, helpful, then do press the like button, share button, and subscribe also. And if you have any doubts or suggestion, you can put them in comment section. I will try to solve them. And also, if you like to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any amount of help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.